Welcome to the part 3 of a conceptual introduction to quantum mechanics. In the last part, we have discussed the wave nature of particles put forward by Louis de Broglie and later detailed by Copenhagen interpretation and other works of other scientists. For example, Max Born was the scientist who associated the wave associated with a particle with the probability of its finding. It's where the probability where this particle can be located. So that idea we need to move forward. Okay. So if there is a wave function, mathematically we call it a wave function, which describes the wave associated with the particle. If we are talking about a wave function of an electron, it essentially means a mathematical entity, a function that is related to the particle such that the probability of finding that particle in space and time is incorporated directly into the amplitude of that wave function in space and time. So usually it is not the wave function itself that is associated with the probability of that electron. It is actually the square of the amplitude, psi square. If we call wave function by the Greek letter psi, it is not psi directly, but psi square that is indicative of the probability. So in quantum mechanics, every particle or every system is associated with a wave function, and the amplitude of that wave function in space and time. The amplitude can vary over time, it can vary over space, and wherever it is, the amplitude will be indicative of the probability of finding that electron, that particle or that system at that time at that location. If I am associated with a wave function, right now the amplitude of that wave function is maximum at this position, at my location, and it is 0 everywhere. And suppose you don't know where I am, and if you ask someone, and someone who knows me tells you that he may be in the office or he may be on the street, that means the wave function is actually spread out over my office and the street. Okay. So that is how you associate the probability of finding a system with the square of the amplitude of the wave function associated with that system. Okay. For particles or for localized objects, obviously we said that only a wave packet can describe the wave function of such a system. Okay. Now it is from this idea that we need to go to the next core idea of quantum physics. There is a paradox involved here. For that, in this slide you can see two scenarios where on the left side you see a wave packet, and on the right side you see a sine wave, a regular sine wave. Okay. So both are wave functions. Assume that these are wave functions associated with the two different systems, and on both sides the red color indicates psi square, while the blue color indicates psi. So as you can see that red color has only positive values, while blue color, which is essentially the wave amplitude, it has both positive and negative values. Now if you look at the probabilities, as we have said, psi square gives you an idea of the probability of finding that system. For the system on the left, you can see that the probability of finding that system is maximum at the middle and it decreases on both sides. But on the right side, if you look at it, you can see that it is a sine wave, it has equal amplitude at different locations of space. Okay. As you can see that for a sine wave, it has equal amplitude over different locations of space. So wherever the amplitudes are equal, the probability of finding that particle is equally there. So what does it mean? It means for a localized system or for a system with a wave packet as a wave function, its location is localized because the probability of finding that system is maximum at a particular location, while if it is associated with a regular sine wave, the probability is spread out. Okay. What does that mean? It means that if for the system on the right side, the wavelength associated with it is very clearly visible, its amplitude is equal at different locations, and that compromises the precision in its location or the accuracy in its location. Whereas if the system is associated with a wave function that is having a wave packet shape, its location is much more localized, or the precision in its location is much more. What does that mean? Do you remember how we came up with a wave function? A wave function was a product of adding up different sine waves of varying frequencies or varying wavelength. So, what does wavelength indicate? Wavelength is directly related with the momentum of the object. Lambda is equal to h by p. So, if a system is associated with a wave packet, that means it is associated with multiple waves that are having different wavelengths. So, different wavelengths means different momentum values. Okay. But a system with a wave packet as a wave function has precision or accuracy in its position, but with respect to momentum, it has multiple components involved. Multiple wavelength means multiple momentum. So, the more precise a position is, the less precise the momentum becomes. Or in other words, if the momentum is not precise, if it is associated with the multiple waves of multiple wavelengths, its position can be more precise. Whereas, if its wavelength is clearly defined, because it has a single sine wave, its wavelength is clearly defined, there is a single wavelength, so there can be a single momentum, but there cannot be a precise position for that. And this leads to what is called uncertainty principle, which was put forward by Werner Heisenberg. Heisenberg put forward a lot of ideas in quantum mechanics, and he was given Nobel Prize actually for inventing quantum mechanics. The description of the Nobel Committee was that for inventing quantum mechanics, and he put forward a lot of ideas, including the matrix formulation of quantum mechanics. And for the time being, we won't go into the details of that. The uncertainty relationship can be mathematically expressed by the equation. It is not an equation, actually, it is an inequality. It shows you delta x into delta p is greater than or equal to h by 4 pi. What does that mean? Delta x implies the uncertainty in position, delta p implies the uncertainty in momentum, and h is Planck's constant. So, the product of uncertainty in momentum and uncertainty in position is always greater than or equal to h by p. So, there should be no chance of confusion here. Uncertainty in this equation does not stand for the uncertainty that we use, the word uncertainty we use in our daily life. Most of the time we say that it is uncertain that it may rain or not. Most of the time we say that it is uncertain for him to come. So, some kind of a doubtfulness is there, but this uncertainty has nothing to do with the doubtfulness. It is not dealing with probabilities, it is dealing with the uncertainty with respect to measurements. Okay, it is actually an error bar we are talking about. So, delta x means that how certain are you, how accurate are you about the position of the system, and delta p means that how accurate are you about the position or the momentum of the system. Okay. So, delta x into delta p, the product of uncertainty in the position and uncertainty in the momentum, it is always greater than a quantity which is h by 4 pi. That means, you cannot improve both of them together. If you increase delta x, the delta p should come down. Or if you are making more and more accurate measurement, delta x or delta p can come down, because if you are trying to measure position accurately, delta x can come down, but at the same time the delta p will blow up, because there is an equality or inequality involved. Delta x and delta p when multiplied together should always be above h by 4 pi. Okay. So, if you consider a car that is moving from Trivandrum to Cochin, at a particular location, say Alappuzha, you will measure the speed of the car, and the velocity of the car multiplied by its mass will give you the momentum of the car. But there is always some amount of uncertainty involved. You cannot say that the speed of the car is 61.7234 km per hour. We roughly say that 64 km per hour, that means it can be 65 or even 66 or even 64.5. So, there is some amount of tolerance or some amount of uncertainty involved in any measurement. So, if you want to make the measurement more and more precise, you want to say that it is 64.73120 km per hour. So, you may have to compromise with the position of the car. You can say that either the car is moving with this much precisely this velocity, then you have to say that the position of that car is somewhere between here and there. Okay. So, for the case of a car, you don't see, you don't feel this uncertainty, because the right hand side of this inequality is h by 4 pi, where h is 6.64 into 10 raised to minus 34, which is a very, very, very small quantity. Only if the left hand side properties like the position or momentum of an electron or a microscopic particle, then only this inequality becomes serious, because h is a constant, it does not vary. That is why we do not see that in our macroscopic world, but this should be kept in mind that this is essentially a result of the wave particle duality that we have discussed earlier. Most of the time people misunderstand this theory, thinking that there is some amount of experimental or technological limitation that you cannot measure both the position and momentum of a microscopic object together, because there is no sufficient technology available. Even at the time of Heisenberg's discovery of this principle, many scientists set out to devise experiments that can precisely measure both the position and momentum of microscopic objects, but the thing is they did not understand uncertainty principle seriously. That is why otherwise they will not have embarked on such missions, because this is not about an experimental limitation or a technological limitation. This is about the very nature of microscopic world, because as we have seen, momentum is directly associated with the wavelength, position is directly associated with the amplitude. So if you want to bring down a wave to a localized object, that means you are actually invoking the idea of a wave packet that is composed of a lot of waves of different wavelengths. Lot of waves of different wavelengths means there are multiple components of wavelengths involved, multiple momentum involved. So it is inherent in nature that you cannot measure them simultaneously and precisely. It does not prevent you from measuring them precisely at different times. You can precisely measure its position at this time, and at another instant of time you may precisely measure its momentum. There is nothing to prevent you from that. Only thing is you cannot measure the position, both the position and momentum of a microscopic object with precision simultaneously. The limitation is applicable only if you are trying to measure them together. Otherwise there is nothing. There are other variables involved, even energy and time and angular momentum and angular position. These are called conjugate pairs of quantities, which equally validates this uncertainty principle. These quantities cannot be measured simultaneously and precisely, accurately together. Now this leads to another idea, interesting idea, tunneling, because there is a wave function involved, there is a probability of leaking certain thing, probability outside. Or if you look at an alpha particle decay, alpha particle is very much bound to an atom nucleus, but you can expect, otherwise you cannot, without quantum mechanics you cannot expect an alpha particle to be outside nucleus. But when alpha particle is coming out of an atomic nucleus, there is some amount of tunneling involved. If you have a wall in front of you, otherwise, unless you have enough energy to circumvent this wall, you cannot move beyond this wall as per classical physics. But in quantum physics it is possible, because of the wave nature of the particles. There is a certain possibility that the wave function can leak outside this wall, so that there is some amount of probability of finding the particles outside this wall also. Same is the case with the potential well inside an atomic nucleus. So that is how processes like radioactive decay and even nuclear fusion takes place. So before 100 years we had no idea how sun is producing energy. Do you know that? Only after the invent of quantum mechanics that we came to an idea, a clearer understanding how nuclear fusion works and sun can produce such immense amount of energy. So without tunneling, this is called quantum tunneling. You can see particles that are normally not expected to be seen as per classical physics. Now if you come back to the double slit experiment, and if you represent the probability of finding that particle on the screen, as this slide shows you, you have an electron source on the left, there is a slit screen on the middle, and there is a screen on the, or the detector screen on the right side. Now you have closed one slit, and what is the probability pattern, intensity distribution pattern you can expect? You can see the intensity peaks in line with the open slit and it dies out on the other two sides. Now if you move the block from one slit to other, now the top slit is open, the left slit is down slit is closed. Now you can see that the probability distribution shifts up. Now the peak is aligned to the open slit which is on the top side. Now, if you open both slits together, you can see the interference pattern. There is a middle band of higher intensity, and there are multiple bands which are called minima and maxima on the both sides of the principal maximum. Now you place two detectors on the screen near to the slits. What these detectors are doing is that they actually see whether the electrons are going through one slit or not. So, the red slit is in charge of the top slit, red detector is in charge of the top slit, and the blue detector is in charge of the bottom slit. Now, if you place these detectors, you are still keeping the slits open, but you do not see the interference pattern. Instead, you see a central maximum and the intensity continuously comes down. There are no bands. What is happening here? The moment you actually detect whether an electron is passing through one slit, it actually collapses or it actually destroys the wave nature of electrons. Okay? This leads to an idea of superposition. Without the detectors, when you allow one electron to pass through the screen with two slits, the electron behaves as if the electron is passing through both the slits. Okay? As a single wave can pass through two slits together, an electron can pass through two slits, because it is associated with a probability wave. That is a wave, it can pass through two slits. That is why it behaves like a wave on the screen, where you can see the intensity pattern as in the form of multiple bands. But the moment you try to detect the electron or measure the position of the electron at a particular slit, the detector is actually trying to see whether the electron has passed through that slit or not. The moment you detect it, the electrons actually begin to behave like particles with a localized position. So, they cannot pass through both the slits together, because at one slit you are being registered. So, you can only be passing through that slit, not through both the slits. So, this is the idea of superposition. Unless there is a measurement, a system can exist in multiple states together, but when you make a measurement, it collapses to a single state. This is called a wave function collapse, which is still undergoing a lot of debates and research in physics, but every debate is concerning how it is happening, not whether it is happening or not. It is happening, but how it is happening, how to make sense out of it. These are our ongoing debates, which is a different area of science, even called the interpretation problem in quantum mechanics. We know that these things are happening, but we do not know how it is happening, and we do not know what is the nature of reality it is trying to imply. So, here is to wind up these ideas. So, we have discussed all the ideas. We have discussed the quantization, we have discussed the wave particle duality, we discussed the uncertainty, and finally we discussed superposition. These four pillars are what keeps quantum mechanics in its position now. Now, for just an exercise, I will give it to you using an uncertainty relationship. First, consider a tennis ball which is having a mass of 60 gram and size of 7 centimeter. It is moving with a speed of 70 meter per second. So, if you use the uncertainty relationship, you can calculate its uncertainty in position and momentum. With de Broglie relationship, you can calculate the wavelength to be 1.6 into 10 raised to minus 34 meter. With that, you can calculate the momentum. And if you know the position of this, if you know the speed or the velocity of this tennis ball to an accuracy of 0.0001 meter per second, it is a highly accurate measurement. Then the uncertainty in position is actually 8.8 into 10 raised to minus 30 meter. 10 raised to minus 30 meter is a very small distance. It is actually a lakh crore portion the size of a hydrogen atom. So, such an uncertainty in the position of a tennis ball cannot be even detected, or it cannot be even imagined. That is why for a macroscopic daily life object like a tennis ball, the wave nature or even the uncertainty in the position is not visible, or even it is not readily apparent. But if you consider that of an electron, it has a mass of 9.1 into 10 raised to minus 31 kilogram, and its speed is 2.2 into 10 raised to 6 meter per second, say, then the wavelength will give you 3.6 into 10 raised to minus 10 meter. Okay? 3.6 into 10 raised to minus 10 meter is actually 4 times the size of an atom. Okay? An electron is a subatomic particle. If the uncertainty in the position of an electron is 4 times the size of an atom, that is actually a considerable amount of uncertainty. Okay? This is how all this difference comes. when you compare tennis ball and an electron, the difference comes because one part of the equation is fixed, which is nothing but Planck's constant. Now, if you assume, if you have some supernatural ability and you change the value of Planck's constant to a very large value, you can see this, you can expect to see strange behavior like a car tunneling through a wall, etc., etc., and a person simultaneously present in his office and his home. This is possible provided you have some trick to blow up the value of Planck's constant to a very macroscopically relevant value. So, until then you cannot expect these strange phenomena to be seen in your daily life. Okay. So, with these remarks we shall conclude the conceptual introduction to quantum mechanics with a quote also, quote from Niels Bohr, which reads, "If you are not shocked by quantum physics, you have not understood it." Okay. So, better luck with your academics. Thank you.